Ventricular Rhythms, Lecture 1, Introduction to Ventricular Rhythm. Our module objectives: define a ventricular complex, define a ventricular rhythm, identify the origin of a ventricular rhythm in the cardiac conduction system, and define the ventricle's role in the pacemaking function of the cardiac conduction system. So ventricular rhythms are the most clinically feared cardiac rhythms because of the hemodynamic instability that they cause. As this lecture will demonstrate, there is no such thing as a completely benign ventricular rhythm. Even premature ventricular contractions, which are generally considered benign, can cause significant hemodynamic compromise in the right clinical setting. So, to define a ventricular rhythm, there's a couple of criteria that must be met. The ectopic pacer must be distal to the bifurcation of the bundle of His. So the ectopic pacer will be found down in the ventricular conduction system or in the ventricular cellular system. And when depolarization occurs in the ventricles, it's going to occur by cell transmission instead of going down the normal electrical conduction pathway. When this happens, the depolarization time increases, which causes a much wider looking QRS. There will also be asynchronous mechanical contraction of the ventricles, so the synctium will not show in this situation. Your QRS complexes are going to be greater than 0.12 seconds, and bizarre ST wave abnormalities due to repolarization abnormalities. So an irritable focus, which is represented by this red star, acts as a pacemaker and causes an impulse to occur. This gives rise to a depolarization wave that radiates outward, if you notice by the different colors, by direct cell-to-cell transmission until all the ventricles are depolarized. Note the color-coded sections of the depolarization wave and the complex. So the color codes here match with the wave. The firing of ventricular ectopic focus leads to formation of wide and bizarre looking QRS complexes. This is just showing an example of the different types of configurations you may see with a wide and bizarre QRS complex, but its actual appearance and location can't really be determined. In addition, the QRS complex will also change in the way it looks based off of which lead that you're looking in on the cardiac monitor. Multiple leads will greatly improve the accuracy of the measurement of the QRS complex. Isoelectric segments may lead to errors in the correct determination of the QRS complex's actual width. Always remember to use the widest complex to take your measurement. So basically this is saying on a 12 lead, we're going to use our widest complex to take our measurement. In lead 2, we're just going to look at our measurement as it appears. In a ventricular complex, ST segment and T waves will always be abnormal and may be inverted, elevated, or depressed. This occurs because of abnormal patterns of repolarization associated with the ventricular complexes. And again, because you've got the cell-to-cell electrical transmission, you're going to have a prolonged depolarization and also a repolarization as well. So what is your failsafe if a ventricular pacemaker fails to fire? You have none. And that's because the ventricular pacemaker feature of the heart is the last resort. It is what is occurring after everything else has failed. So P waves are very useful in evaluating the wide complex rhythms, especially in ventricular tachycardia. They're not going to be normal. You need to concentrate on the morphology and the axis, which is going to be, is it above or below, and rate of the P waves. The PQRS relationship should also be closely examined in wide complex rhythms. Normal P waves may conduct but fail to capture the ventricles. And so again, you've got your own ventricular pacing, but the P wave may still be pacing. The P wave may be blocked at the AV node, in which case it will not appear in front of the ventricular complex. And AV dissociation is very common with ventricular complexes. The P wave can be retrogradally conducted to the atria, and this will actually cause you to see retrograded or inverted P waves in leads 2, 3, and AVF if they're there. And they're not there in a lot of the situations. This figure illustrates ventricular conduction through the AV node. In one graphic, the P wave is blocked, and in the other, the impulse is retrogradally conducted to the atria. And if it's blocked, you may not see anything. If it's retrograded, you may see it, but you would actually be looking at a inverted P wave. Normal P waves may conduct but fail to capture the ventricles. Retrograde P waves seen in 2, 3, and AVF, and a very long RP interval in most cases. And remember, the RP interval is that rare occurrence when you actually have the P wave post QRS. And the QRS could also be buried. And this is the RP that I was talking about. It can often be long because it takes time for the cell-to-cell transmission of the ventricular impulse to reach the AV node. The further the ectopic pacer is from the AV node, the longer the RP interval is. When the AV node is not conducting, it creates functionally a complete block at the level of the interventricular septum. The atria and the ventricles are completely oblivious to each other, and you've heard this before in AV dissociation with a third-degree AV block. And two separate pacemakers develop, and each pacemaker will keep its own intrinsic rate and control its respective chamber. This image illustrates how each pacemaker will keep its own intrinsic rate and control its respective chamber. AV dissociation occurs because there's no coordinated electrical activity between the atria and the ventricles. So we haven't really mentioned this a lot, and it's not something that we're going to particularly be looking for in entry-level cardiac interpretation, but Josephson's sign refers to the presence of a notch in the downstroke of the S wave, and it's going to show in many complexes of the ventricular origin. The presence of this notch is very useful in distinguishing a ventricular complex from an aberrantly conducted supraventricular complex, or a complex with the underlying left bundle branch block or right bundle branch block. And Brugada's sign refers to the distance of at least 0.10 seconds from the onset of the QRS complex to the very bottom of the S wave that is present in many complexes of ventricular origin. The presence of this distance interval is a very useful sign in distinguishing a ventricular complex from an aberrantly conducted supraventricular complex or a complex with the underlying left bundle branch block or right bundle branch block. And so, as we move forward, in order to determine our different types of ventricular arrhythmias, we're going to look at the rate of the wide complex rhythm and determine what we're going to call it based off of our rate. Also, the hemodynamic status of the body is completely dependent on this rate and the appropriate contraction of the ventricles. Wide complex rhythms are generally dangerous and should be treated with extreme urgency and care.